Hello everyone, and welcome to this video, the 25th in this series. Now, this video looks at some plots of geodesics using the Mathematica notebook developed by the authors of the paper listed below. Now, I've done a couple other videos in the same vein by these authors, the three of them. Their paper is published here. This will be included in the video description below, so you can go to the link and have a look yourself. The Mathematica notebook they've developed has been made publicly available here, and that'll be in the link in the description below, or this link will be in the description below the video. And now this particular video is just going to focus on examples of null geodesics. All right, now the paper can be found here. These Kerr geodesics in terms of Weierstrass elliptic functions. And I'm going to give you shortly, in a couple of slides, a very, very brief rundown on this method. You'll be much better off going and having a look in the actual paper itself and seeing for yourself. All right, but anyway, you can find the paper here. Here are the researchers here: AdamCieslik, Eva Huckman, Patrick Muck. I hope I pronounced those correctly. If not, I apologise. All right, you can locate the Mathematica notebook here. All right, and one other thing, when you do download it, if you do have Mathematica, that is, if you do download the notebook, just bear in mind it's best to put the package in the same directory from which you run it. So to use the library of Mathematica, put this package here in the same place as the notebook you work in or work with. Okay, there's a demo notebook included that gives you examples of how to do things, and a couple of videos here I've shown you as well. Okay, so let's have a look. Yeah, so just keep the files together in one folder and launch your Mathematica notebooks from there. So keep it all in one folder and launch your Mathematica notebooks from there. All right. Yeah, it's a great paper. It's a fantastic piece of work. What they've done there to be able to plot the geodesics, it's a wonderful job they've done, and all credit to those three researchers. All right, now briefly, let's see, I'll put that there. So you have your equations of motion here like this, and I've derived these over a couple of videos, about 4 or so videos on this channel. And then what they do here on the left-hand side is they've done a rescaling of coordinates so that rho squared dx mu d tau becomes dx mu ds. S is a time parameter. So tau, or in other words, is the integral 0 to s bar rho squared ds. You can just by rearranging this, take that over the other side there, that over there, you get rho squared ds, then integrate both sides. And so you can replace the left-hand side here with this, dr ds. So we now have these first order differential equations. Okay, and then we can actually go just one step further. The next step then is, this is a brief rough overview, sorry about that, but just give you a brief idea of what they're doing. Okay, next step then is rescaling to dimensionless variables, just like this, including mino time. S bar is one on mass of the black hole, mass of the particle you're referring to if you're talking about particles of mass. And then the equations become appropriately changing variables. So zeta here, d zeta ds instead of the dr ds that we had on the previous slide. And the others suitably turned. Don't forget r tilde, theta, capital theta tilde, capital R tilde of this takes this form here as a result of that rescaling. And so these are the equation of motion we're going to solve, and this is where the Biermann-Weierstrass theorem now comes into play. So I'll go to the next slide. So now we use the Biermann-Weierstrass theorem to write the R tilde as this fourth order or quartic polynomial, where these constants here, okay, in our case there. Now, from that theorem, let's say we pick a segment of that trajectory, then the time is the integral dz square root of this, okay? Epsilon r is just the direction. It has a value of +1 for outward geodesics, -1 for inward geodesics. And so from there, okay, that's the this is the time parameter. And we have here, I'll just move that. We have here the Weierstrass invariance, have these forms, and that's due to the Weierstrass theorem. You can now solve these first order differential equations using these quartic polynomials, which have the form mentioned earlier. And so the solution becomes, remember our first one, zeta of s, s was the time parameter, zeta of s becomes some initial value plus all of this, where these Weierstrass functions have this form here. Remember gr2, gr3, and the time parameter s. That's a very brief overview. Please go look at the paper itself, read it for yourself. But just roughly, thanks to the Biermann-Weierstrass theorem, some very good solutions can be found to the problem of geodesic motion around a Kerr black hole. All right, so let's have a look at some examples. You have some constants. Phi is the azimuthal angle, and in all these examples, I'm just going to use phi as 0.33 radians. This is the initial starting point. So with this solution, you need the initial starting point, and then some things like the energy parameter, the conserved angular momentum about the axis of rotation, that's in the azimuthal direction, and then the kappa parameter. So the energy parameter epsilon, the conserved angular momentum about the vertical axis, and the kappa parameter here. Delta is 0 in all cases for this video because we're dealing with null geodesics. A is the spin parameter of the black hole. That's the angular momentum per unit mass. And so phi is the azimuthal angle where we're starting, so 0.33 radians. Epsilon r -1 means it's an inward bound trajectory, so it's starting up here and coming inward. R00 is starting 25 units out. So the starting location is 25 units out. Epsilon th is +1 means, and that's measured, this is the polar angle direction. Either we're going in the positive direction, down, from the positive direction of the z-axis, going down, and minus is going back up again. Okay, in this case, it's going down. So we have a trajectory that's at 0.85, th00, 0.85 radians, measured with respect to the positive direction of the z-axis here, and 0.33 radians measured with respect to the positive direction of the x-axis, okay, starting 25 units out. And we will use those values, phi, all of these, during the course of this video. The only thing we're going to vary, the angular momentum, kappa, sometimes the spin, and the energy parameter. They're the only things we're going to measure, to vary, sorry. Everything else will be constant. So here's an example of a flyby orbit, okay, for these values using the notebook. Maybe I should move that. And let's have a look now at some other examples just briefly. Okay, so here is a deflection orbit. So we've started over here, inward bound, epsilon r -1. Okay, starting 25 units out. All right, and the epsilon parameter is 1. The energy parameter is 1. Angular momentum about the vertical axis here of the photon is almost 0, so not quite 0. Right? And when we do that, and kappa set to another constant set to 60, the spin of our black hole is 0.8, which I often like to use on this channel as my example. And we can see here's the geodesic followed by a photon around here and the back. It's quite impressive. Let's have a look at another example. So that was a deflection orbit. Here's another deflection orbit. Here, this time we changed the angular momentum of the photon about the axis of rotation. 3.0 we set it to. Epsilon parameter is still 1. As kappa we've changed. Okay, it's a combination of variables which you can read on the paper there, but it's another constant of the motion. And you can see it starts out about here and comes in round this way, like that. So there's another deflection orbit. We can get different orbits by varying these parameters. Here, the parameter the angular momentum of the photon about the axis of rotation is 0.05, getting very low again. Kappa is 60. Otherwise, everything else has stayed the same. You can see it sort of starts out here, comes down here, then does this little sharp turn here. This is the projection on the XY axis from above. If I were to put this on the screen for you, you would see that this geodesic here is actually on the other side of the x-axis. In the three-dimensional view, it's a bit of a visual trick here, but it looks like it's on this side of the black hole, but it's not. It's actually on the other side. If I could tilt the z-axis towards the screen, towards us, or towards you, the viewer, you would see that's actually on the other side, just as it is here. Notice a sharp kink here due to the frame dragging the space-time in this area. We'll have a look at that a little bit further by varying the angular momentum. All right, next example is I've lowered the angular momentum of a photon almost to 0. So the last slide was 0.05 in the positive direction. I've lowered it down now to 0.01. It's sort of testing the limits of the program. You're starting to get these sort of straight lines because it's integrated. The program's integrating near turning points. So that causes a bit of a difficulty. Otherwise, everything else has stayed the same, but it just sharpens this point here. So you can suspect that something's happening as we get down to 0. We should probably expect maybe something to happen. Look how sharp that turning point is. Or getting sharper than the previous slide anyway. So let's have a go. Next one now, getting down 0.05, got even lower. Still very sharp. Something's happening there. All right, all the other parameters have stayed the same. So I think the next one is, yes, 0 self. So give the photon starting out here at 25 units here, give it 0 angular momentum about the axis of rotation of the black hole in that direction there, and look at this. And it just bounces back out again. Comes in there, simply because it's got 0 angular momentum, everything else has stayed the same. Still starting at 25 units out up here, and it comes in and then shoots out again. All right. Next one. Now, let's try varying the spin of the black hole, say from 0, Schwarzschild case, up to extreme Kerr 0.99. And when we do that, lambda is 0, A is 0. This is our Schwarzschild case. There's no spin on the black hole anymore. There's a singularity at the center. And what we've got is just, this remains like this. Now, it's a bit of a trick because from looking from above, from the positive z-axis down, projected on, it looks like it's all sort of gone straight back out that way. But in the three-dimensional case, it doesn't look like that, but it actually has. All right. Bit of a funny result. I would have thought the photon would carry on straight on through, but anyway, that's what happened. Let's look at the next one. Now, the spin of the black hole is 0.1, and we can see it's deflected out. All right. 0.2, and the opening angle, the projection in the XY plane has the opening, there's starting to be, the angle is starting to open between these two. 0.3, 0.4, 0.5, 0.6. You're really starting to see the inner event horizon now, the faster it spins. 0.7, see how the inner event horizon's grown larger. 0.8, 0.9, inner event horizon's got larger here. And then 0.95, well, it's getting larger. And 0.99, look at that. And that's as high as I went there with that one. Now let's vary the energy parameter epsilon of the, when I say of the black hole, I'm talking about in relation to the photon. This is the energy parameter of the photon, just varying it. You expect the energy parameter to be 1, but anyway, just argument's sake, what does it look like if we just vary it? All right, so it's not the black hole, it's the energy parameter of the photon. My apologies for that, I should have edited that more carefully. Okay, so here we go. from a distance there, zero angular momentum on the photon, and here we go, epsilon parameter 0.1. It doesn't seem to, that's about as much as it plotted. And here we go, in like this, out. Now this is this energy parameter we're varying it, but the black hole spin is 0.8. So on the same one here, 0.8, it goes back out again. Okay, so 0.8 for all of these. So it's quite a fast black hole. It's quite a high spin rate, but it's just pushing the photon back out. Okay, you can see it's just pushing it back out again. Yep, see 0.3. This is closing up here, 0.4. No, 0.8, sorry. Sorry, 0.5, sorry for the energy parameter. I lost track of where I was then. 0.7, 0.9, 0.95. So it's just playing around with what happens. You expect the energy parameter to be 1 though, wouldn't you? But you're releasing a photon from there. But anyway. And then just finally, it's a wonderful program. You can play with yourself. And that was the point of showing it today. You can put in different parameters. You could vary them and play for yourself, or vary combinations of them. It's up to you. I just think it's a wonderful bit of work these researchers have done to produce something and make it publicly available like that. And it gives everybody a chance to imagine. In this case, in this video, I've focused on photons only, but in previous videos, I've looked at particles with mass. What sort of trajectories do they follow? What do their geodesics look like? But this photon here, I mean, a wonderful example. It's it's amazing to think. This is how light moves around a black hole, around a spinning black hole. It's just fascinating. Anyway, that's it for today. Thank you very much for watching. I hope you enjoyed that, and I'll see you in the next video. Okay, take care, everyone. Bye.